You know the frustration, right? An AI makes a decision, maybe denies a loan or suggests a medical path, but you have absolutely no idea why or how or what factors really mattered. It's like asking a magician to explain the trick, and they just shrug. We talk about AI as a black box all the time. Powerful, sure, but fundamentally opaque.
It's a constant challenge.
But what if that whole problem could be flipped on its head? What if the system itself was designed to be transparent from the ground up? There's this bold new claim about a framework that could redefine AI.
Right.
So, our mission today, let's dig into this revolutionary computational framework. It supposedly not only processes information incredibly fast, but also intrinsically explains itself. Every operation is transparent.
Yeah.
Imagine a computer that literally shows you its reasoning, step by step, no extra tools needed.
What's really fascinating here, this isn't just, a small improvement to make AI a bit clearer. This challenges our core assumptions about computational understanding itself. It's really a fundamental rethinking of how computers process information and, maybe more importantly, how they explain what they're doing.
Okay, right. So let's unpack this black box problem first, just to set the stage. Traditional AI, especially things like neural networks, they're incredibly powerful. We know that.
Absolutely.
But how they get to a decision, still largely a mystery. If you try to peek inside, you find, what, millions of parameters?
Millions, sometimes billions, and they're just numbers. Abstract numerical values.
Like a weight of, say, 0.73 buried deep somewhere, maybe at location 2341,567. That means, well, it means nothing to a person looking at it.
Exactly. It has no inherent meaning on its own.
So the actual why behind an AI's decision is just scattered across these huge, incomprehensible matrices, like tiny breadcrumbs that don't form a path.
Spread out everywhere.
So what have we been doing about this? You mentioned tools before, right? Like SHAP and LIME. What's the deal with those?
Right. So in the field of explainable AI, or XAI, we've developed these quite elaborate tools. SAP, that's Shapley Additive Explanations, and LIME, Local Interpretable Model Agnostic Explanations.
Okay.
They essentially try to reverse engineer the meaning after the AI has made its decision. They kind of poke at the box from the outside and make educated guesses about which inputs were most
So
important.
their interpretation's not the real thing.
Precisely. They're always approximations, estimations. And they often leave frustrating gaps in understanding, which, raises a really important philosophical question.
Which is?
If the explanation is always just an afterthought, this separate interpretation layer built on top, how can we ever truly, fully trust the execution itself?
Right.
Traditional computing has always had this strict separation, this duality, between execution, what the system actually does, and explanation, a separate process, trying to make sense of it later.
They're two different worlds.
Fundamentally different activities, yeah. Always needing some kind of translation layer between them.
That sounds like a major limitation. But, I mean, isn't some level of black box just inevitable when things get this complex? Are we really saying this new framework gets rid of it completely? Or just, makes the glass a bit less foggy?
Well, that's exactly the core claim of this new approach.
Yeah.
It's built on something the sources call the FIM Factor Importance Mapping Unity Principle. And it introduces a really radical idea.
Okay, what's the idea?
The idea is position is meaning.
Position is meaning, not just contains meaning.
No, not contains it, not points to it. The physical position, the memory address itself, is the semantic meaning. Let that sink in for a moment.
Okay, so give me an example. If the system goes to, position 1 in its memory.
It doesn't just mean fetch data at address 1. It inherently means I am now considering the most critical factor for this specific context.
Wow.
And if the system then moves through, say, positions 1 and 47, then 203, that sequence, that path it takes through memory, that is the reasoning process. It translates directly to. First, I prioritize the critical factor, position 1. Then I checked a secondary factor, position 47. Then I validate it against an edge case, position 203.
So the navigation itself is the explanation.
Exactly. The access pattern is the explanation. It's built in, inherent, not added on later.
Okay, that really changes things. That collapse of the explanation-execution duality you mentioned?
It's philosophically pretty profound, yes.
Yeah.
With this FIM Unity principle, the mantra becomes execution is explanation.
Execution is explanation.
The act of fetching data, say at position 47, that single operation is simultaneously three things. It's a computational step. It's a semantic statement. I'm considering moderately important factor, hashtag 47, and it's an explanatory act because its position tells you its importance rank relative to everything else.
No translation needed?
None whatsoever. The operation explains itself in real time.
This really does sound like the death of the black box then. Because in, normal systems, if a neuron fires at some technical address like 0x7FF8000, that address tells you nothing about why. You need statistics, complex analysis later on to guess the meaning.
Right. Post hoc reconstruction.
But here, with position as meaning, every memory access is semantically loaded. That same address, 0x7FFF8000, could inherently be the concept heart disease risk factor. The box isn't black, it's glass. Because the very structure is the meaning.
And if we connect this to the bigger picture, it starts to tackle a really thorny philosophical problem. Computational intentionality.
How physical stuff can be about something.
Exactly. How can bits and bytes, physical states, be about concepts like risk or importance? In traditional systems, meaning is imposed from the outside by us. But here, the system's navigation through this semantically structured space is its intentional behavior. Accessing medical emergency at position 1 isn't just arbitrary, it's an intentional computational act signifying criticality.
Okay, so this leads to something mentioned in the material called the explanatory completeness theorem. How does that work?
Right, it highlights the difference quite starkly. Let's take that loan denial example. With traditional AI, the execution might look like access memory address, 0x1234, then do some computation, then output, loan denied.
Right, standard process.
But the explanation, it's full of holes. Maybe access 0x1234 might have used customer age. Reason unclear. Result, loan denied. You see, massive gaps. You need an interpreter to fill them in, often imperfectly.
Lots of question marks.
Now, contrast that with the FIM Unity Principle approach. The execution trace is the complete explanation. It looks like this. Access position 1, credit default. Access position 47, recent bankruptcy. Access position 203, insufficient collateral. Result, loan denied.
So you see the exact factors in order of importance.
Precisely. The trace itself tells the whole story. It's human-readable, directly auditable, complete explanation, no gaps.
That's incredibly powerful. But, okay, there must be some clever technical trick here. What exactly is this short rank thing, and how does it manage to bake meaning into position? Others haven't done that, right?
Right. Short rank is the core mechanism that makes this possible. The absolute key requirement is what's called importance-based addressing.
Importance-based?
Meaning the semantic importance of a piece of data literally determines its physical location in memory. So position 1 isn't just the first slot. It means this is the single most important factor for this specific decision.
And importance isn't just subjective.
No, it's objectively measurable.
Yeah.
Sources mention calculating it using factors like frequency X, criticality, EGPACT. It's quantifiable based on the data and the context.
Okay.
And this is what makes short rank unique. Think about other techniques. LSI or word2vec. They tell you words are related. They put similar things near each other. But position itself doesn't have a fixed rank or meaning.
Right. Proximity isn't rank.
Exactly. Knowledge graphs show relationships, connections, but again, no inherent importance ordering in the structure itself. And hash tables. They just scatter everything randomly for fast lookup, destroying any semantic structure.
So short rank is the only one where position equals importance rank.
As far as the sources claim, yes. It specifically encodes decision importance into the physical address.
Yeah.
And it's not just a clever hack. There's a mathematical foundation. They talk about this Unity Principle, SP and H.
SPH.
Optimal semantic organization, S. Optimal physical memory layout, and optimal hardware access patterns. The mathematics apparently shows these three things become identical. They unify under this framework.
Wow.
That mathematical identity is what allows this direct near-instant access. We're talking O1, complexity in computer science terms, always fast.
Instead of searching.
Instead of searching through trees or lists, which is O log n, gets slower as data grows. This is fundamentally faster because of the semantic structure.
Okay, the theory sounds amazing, but let's get practical. What does this actually do in the real world? What are the, the tangible benefits?
This is where it gets really interesting.
Yeah.
First, performance. Just raw speed. The claims are significant. An 8.7x to 12.3x performance improvement over traditional methods.
8 to 12 times faster. How?
And alongside that, incredible 99.7% cache hit rates, which basically means the processor almost always finds the data it needs immediately.
Okay, why so fast?
It's a combination. The biggest factor is superior cache locality. because related important things are physically close together in memory. That alone gives a 3.8x boost.
Makes sense.
Then you eliminate all the translation overhead. Short rank is direct O1 access, no searching. That's huge. Plus, better branch prediction for the processor, 1.0x, and more efficient pipeline usage, 1.26x. Every part of the hardware works better because meaning and physical location are aligned.
So speed is one thing. What else?
This is crucial. Hardware-validated trust.
Hardware-validated trust. What does that mean?
It means you can objectively measure if the system is doing what it says it's doing in real time
How?
by monitoring the processor's own performance counters. Things the chip already tracks, like L2 cache misses, branch mispredictions, pipeline stalls. If the system claims it's accessing important data, low position number, the hardware should reflect efficient access. If there's a mismatch.
Something's wrong, an error, or tampering.
Exactly. You get an objective, quantifiable measure of computational integrity. And the detection is incredibly fast under 1 microsecond latency, critical for finance, medical, anything high stakes.
Oh, less than a microsecond?
Yeah, the trust calculation is literally based on the difference between the expected hardware behavior, the SAY, and the actual measured behavior, the DO1 SADOC, quantifiable trust.
That's incredible. Okay, think about legal situations. Legal discovery. Instead of lawyers sifting through gigabytes of cryptic logs, you just provide the access trace. Positions 147203.
That's the idea. If the question is why was this loan denied, the answer is baked into the trace. Position 1, the primary reason, indicates high credit default risk.
It's inherently explainable, even to non-experts, like a jury.
That's the claim. Because importance is built in. The sources suggest this could cut legal discovery costs by as much as 99%.
99%. That's transformative for transparency and accountability.
Huge implications for regulation, too.
And you also mentioned something about human cognition.
Yeah, fascinatingly, there's a parallel. We humans tend to remember important things more easily.
Yeah.
Right? They feel closer, more accessible, almost like they're in position 1 of our own memory.
That's true.
And when we explain things, we naturally start with the main point, then add details. First, the main reason was X. Then there was also Y. It follows an importance gradient. This system seems to mirror that natural cognitive process.
And quickly, you mentioned distributed systems.
Right. Briefly, because importance ranks are inherently comparable, systems can coordinate decisions much more efficiently. They can correlate their ranked lists, reducing the need for complex, message-heavy consensus protocols by potentially 90–95%. Makes distributed systems faster and more reliable.
Okay, so massive speed, built-in explanation, hardware trust, legal transparency. Where can we actually see this making a difference? Let's talk applications. What does this mean for, you listening if you're running a hospital or trading stocks or doing legal work?
The examples given are pretty compelling.
Let's hear them, like medical diagnosis.
Imagine an emergency room. Critical decisions needed fast. This system is described as processing over 68,000 standard medical diagnosis codes, the ICD-10 codes, in under half a millisecond.
Wow.
Leading to a claimed 94.7% accuracy in identifying the correct primary diagnosis and making the whole differential diagnosis process 8.7 times faster. In an ER, that speed could genuinely save lives.
Absolutely. Okay, what about financial analysis? High-frequency trading.
Speed and trust are paramount there. The claim is less than 2 microseconds to perform complex correlations across potentially 200,000 plus market patterns.
2 microseconds.
With that sub-microsecond hardware integrity check running alongside 567 nanoseconds they specify. The bottom line, a 12.3x improvement in how fast trading orders can be executed.
Huge edge. And legal document processing. You mentioned discovery costs.
Right. Beyond just discovery, think about research. Accessing and ranking relevant information from, say, 150,000 plus legal precedent categories in under 100 milliseconds with 92.1% precision. They estimate this could lead to a 74% reduction in the manual time lawyers spend on research and make analyzing case law 12.3 times faster. No more drowning in documents.
Big change for legal teams. One more, supply chain optimization.
Yeah, managing complex global supply chains. The system could apparently perform complex rebalancing across 50,000 plus product classifications in under 5 milliseconds.
Dynamic adjustments on the fly.
Leading to an estimated 18.7% improvement in total supply chain costs. Better efficiency, less waste.
Okay, those numbers are pretty staggering across the board.
If we connect this to the bigger picture again, It's not just about doing things faster. It's about enabling a whole new class of systems that are inherently transparent, demonstrably trustworthy, and highly intelligent all at the same time. That combination unlocks possibilities in critical industries that just weren't feasible before.
It really sounds revolutionary. Which brings up the obvious question. If this is so groundbreaking, why haven't we all heard about it before? You might be sitting there thinking, this sounds, frankly, almost too good to be true.
And that's exactly one of the key reasons the sources mention for why it's been perhaps a quieter revolution until now.
Too good to be true.
Yeah. The very claim execution as explanation seemed almost philosophically impossible to many researchers, steeped in that traditional execution-explanation duality we talked about.
It goes against the grain.
Completely. It fundamentally challenges decades of work in AI explainability, basically suggesting that maybe many were trying to solve the problem in a fundamentally different, perhaps less direct way.
Okay, what else?
It's also subtle. The core distinction position contains meaning versus position IS, meaning it sounds like semantics, like wordplay. But it's like the difference between using a map to navigate versus the map being the territory itself. When position is meaning, the structure is the reality. That subtlety is easy to overlook, but the implications are profound.
Right, a small change in concept, huge change of outcome.
Exactly.
So, wrapping this up, what's the main takeaway here? This deep dive seems to show a potential world where complexity in AI doesn't automatically have to mean opacity.
That seems to be the core promise.
And it hinges on this powerful, if subtle, idea. When position IS, meaning execution, IS explanation, no translation required. It feels like more than just clever engineering. It's like a fundamental shift in thinking about what computational understanding even means.
It really is. And it leads to one final, pretty provocative thought from the source material. They suggest that by forcing semantic importance to perfectly align with physical position, they may have, perhaps unintentionally, stumbled upon something related to, well, computational consciousness.
Consciousness, how so?
In a very narrow sense. The system no longer needs a separate process to explain what it did or why, because doing the sequence of accessing importance-ranked positions is the explanation. There's no gap between action and awareness of the reason for action, at least in terms of the system's own operational logic. What it did is its reason.
Huh. Think about that. A computer system that doesn't need interpretation because its actions are its reasons transparently, instantly. What questions does that spark for you about the future of AI and how we might interact with machines that can, in essence, show their work inherently?